So good morning, good afternoon, good evening. Thank you very much for joining us today for another interesting talk that today will be done by Professor Elkim Roa from Universidade Industrial de Santander in Colombia, talking about hardware security instance to secure IoT sensors. But before doing an introduction about Elkim Roa, I just will do some brief announcements. So next week, it's not yet sure that we are going to have a talk because there was a little change. But if you want to join us today, the chapter of CASS at University in Lima is celebrating their 13th anniversary, and they have a set of talks. So I will do the first one today, 4 p.m. in Peru. That means GMT -5. And then there will be also, after my talk, a talk by Professor Carlos Silva and by Fernando Silveira from Uruguay. So this is for your happy hour of today. Then July 22, we are going to do the first industrial talk, 2021. So you have a set of 20 talks, recorded versions from last year that are available in our YouTube channel. And the talk next to will be done by Alan Wong, from Director of Engineering at Ensilica in England, talking about enabling the next generation of always connected cars. And it will also be done in the announcement of Ensilica Brazil by Dr. Júlio Leão, because Ensilica just opened a branch here in Brazil at Porto Alegre. By the way, soon you are going to see the announcement of another international company that is also opening an office in Porto Alegre. So this will be on Thursday, July 22. And the day after, we have another CASS talk by Dr. Vladimir Alves, that is CTO at NGD Systems, talking about computational storage and its application for machine learning. So Vladimir, I'm sure that you are going to like it because the subject is a real interesting one. And so I hope to have your participation also. Then August 13 is Luciano Agostini, professor from Federal University of Pelotas, Brazil, talking about video coding, state of the art and trends. So this I'm showing the talk, the future talks that we have the flyers already, but there is some others that are being scheduled between then also. Then if you lost the special event organized a few days ago, the meaning of assessment in higher education and research, that there was a talk by Professor Michel Robert and a panel with Raimundo Macedo, Marcelo Lubaszewski, Thiago Bali, and Avelino Zorzo. So the recorded version is already available in the YouTube channel of CASS Rio Grande do Sul chapter also. So this was a very nice session. Then also, if you lost some CASS talks from 2020, 2021, the recorded sessions are available also in the CASS Rio Grande do Sul YouTube channel, and much more, as also the talk that Elkim has done in the microelectronics school last year is also available there. So there is about more than 90 talks that are available for you in very interesting topics with excellent speakers. Also, I would like to remind you that we are approaching to the deadline for the next LASCAS, the flagship conference of IEEE CASS Society in Latin America. That means the International Conference of CASS in Latin America, open to people all around the world. The deadline is September 1st. So you have July and August to finish your papers. And now something that is working very well is that a set of best papers are selected to be published in Transactions on Circuits and System 2. And in this case, the paper will appear in the edition of the journal in the month of the conference. And then in the proceedings of the conference, you are going to see just the abstract, because the full paper will be in the journal. Also, during the conference, there is an extra evaluation of the presentations, and a set of best papers are selected and invited to submit the extended version to the special issue in TCAS 1 related to LASCAS. So this is an excellent path to have a good paper in a good journal published in a faster way. No? And LASCAS 2023 will be in Ecuador, and 2024 will be in Punta del Este, Uruguay. Also, the microelectronics graduate program here in south of Brazil has the registration for the master open till next 17 July. So people from all around any location outside of Brazil is also welcome. There is some scholarships for this. And also is always open the registration for the PhD. And in this case, it's continuous opening. So you can start your PhD any month of the year, depending on your interest. Also, you have now, I don't know till when, but using the code Future50, you can do your membership as a student or graduate student in IEEE with 50% discount. So, but we are here today to attend the talk by Professor Elkim Roa from Universidade Industrial de Santander in Colombia. So he has a set of very nice, interesting works there. But today he's going to talk about hardware security instance to secure IoT sensors. And Elkim received his PhD degree in electrical and computer engineering from Purdue University in USA, where he was a Fulbright scholar, his master's degree from the University of São Paulo in Brazil, and his bachelor's degree in electrical engineering from Universidade Industrial de Santander in Colombia. From 2014 to 2016, he was with Rambus Inc., where he has engaged in high-speed servers front-end design. Since 2016, he has been an associate professor at Universidade Industrial de Santander in Colombia. His research interests include circuits and architecture design for security, front-end circuits for high-speed interface, and low-energy and efficient computing. Elkim currently serves as a technical program committee member of the IEEE Custom Integrated Circuits Conference, IEEE CASS technical committee member of Power Energy Circuits and Analog Signal Process. So thank you very much, Professor Elkim, to accept our invitation to give this talk today. And the floor is with you to start your talk.
Thank you so much, Professor Ricardo, for inviting me. So this talk is about hardware instances to secure IoT sensors. In this talk, we are going to first try to motivate the work that we are going to present. We also are going to talk about glitch attacks in microcontroller units, particularly glitches attacks, supply voltage attacks. And there, I'm going to talk about encryption accelerators, particularly an AES-256 bits model accelerator, working as a peripheral within a microcontroller, and also a physical unclonable function using no-volatility random access memory macros that is also instantiated in microcontrollers. So let's start with the motivation. So let's talk about the IoT security problem. In network sensors in transportation systems, power grids, and industry made an estimation of 25 billion installed devices in the world. The network security is as safe as the installed sensor nodes. So you have one sensor node that is vulnerable, you have the whole sensor network vulnerable. Okay. Now, let's talk about there are two different types of attacks. There are software attacks and there are hardware attacks. We are going to focus in this presentation to hardware attacks and hardware solutions to enhance security in within system on chips. So there are several hardware known attacks. In particular, side channel attacks employ supply, clock, and interface vulnerabilities to get access to devices. There are two types of side channel attacks: active and passive. Active attacks are more related to attacks that are when you are injecting some kind of variable. Like for instance, in this case, overheating. You are hitting the device. You might be able to see some vulnerabilities within the systems. For instance, might be able to jump on in some security layers of the microcontroller. There is another one that is optical. So you can inject attacks using optical by decapping the chip, decapping the microchip, and try to inject some optical attacks in order to see what kind of vulnerabilities the hardware has. There is another one that are the electromagnetic attacks, where you can also try to attack by injecting some electromagnetic waves. And there is also the underfeeding, which is the decreasing or the decreasing of the voltage supply, or in other cases, also maybe changing the clock signal of the system. You can also have underclock or overclock in order to change the frequency of the microcontroller, and therefore may also try to break the system or the operation of the regular functionality of the microcontroller. And then the last one, but not the least, are the glitches. So you can inject glitches, for instance, in the supply voltage network in order to see how the microcontroller responds. We are going to focus on, in this first part of the presentation, on glitches attacks and also on how prevent them in current microcontrollers. So there are also the passive attacks. Passive attacks are more related to gather data and do some offline post-processing. So you can, for instance, take data from differential power analysis and try to see what kind of vulnerabilities the system might present. So in this talk, again, we are going to focus on hardware security instances and system on chips or microcontrollers. So we are going to see how we can implement some peripherals to enhance the security of the system on chip. We are going first try to see how we can attack a microcontroller that it was supposed to work functionally without any bug, but then we might see that there are just functional bugs because the nature of the circuits within this microcontroller. Then we are gonna talk about secure instances like an encryption mode, how to accelerate the encryption mode without increasing the energy and also without adding on additional vulnerabilities. And the last one, we're going to talk about physical and criminal functions and how these functions can be implemented within a system of chip. So let's talk about glitch attacks in microcontrollers. So you can have an attack in the power supply line of a microcontroller. In this case, we're using one of the microcontroller designed in our group. By the way, the first RISC-V system on chip in the world in 2000 that we measured in 2015. And since we have all the data and all the knowledge of the circuit or the circuits that we use in this microcontroller, even the architecture, we can see what kind of vulnerabilities we are rising by attacking the power line of the microcontroller using glitches. we're going to try to show an example of a instruction jump. So just imagine that you have this microcontroller installed in one system where you have two or three different type of user privileges, and you might want to jump in those user privileges, or just by jumping in the when the system is asking for the password. Because imagine that you are attacking the supply lines by glitching the supply lines, glitching the voltage, and you might jump the instruction of the system when it's asking for the password, and then you get access to the system. So we are taking advantage of the microcontrollers that we have. We have actually 3 generations of microcontrollers in our group. So because we know all the details, all the implementation details of the microcontrollers, we are able to see what is going to happen to the microcontroller, to the system, in the circuit level, in the architectural level, when we are attacking it by using glitches. So we are going to show you some results with the first microcontroller that we developed here, the 2PR, which is the more the simple one. So this microcontroller has a core. It's a small core. It's a PQRB32 related microprocessor, RISC-V microprocessor, and the peripherals are interconnected using an AC4 bus. We have connected GPIOs, SPI interface, and data converters also within the APB bus. So the goal here is try to inject to the supply of the microcontroller a glitch. And we are going to use an underfeeding. So we're going to try to decrease the energy of the voltage supply by just pulling the voltage supply of the microcontroller. And the goal is try to jump in loops. So we have here, for instance, we put the microcontroller in infinite loops, and we are trying to break those infinite loops by glitching and see what's happening in the microcontroller. In order to do that, we employ well-known system in the Huawei domain for doing this kind of attacks. We are using the chip whisperer board that let us kind of not just push the glitches, but also to read all the details of the microcontroller that we are in, with the one which we are injecting the glitches. So again, here is the sample that we are going to do. We are going to try to see what will happen when we glitch the microcontroller in infinite loops. So here are some results. Here we are kind of dumping the output of the microcontroller, and also we even can put the output within the GPIOs using LFDs. But here we are just dumping the output constantly during live glitching, and see that we are definitely jumping the infinite loops, and we just jump and we keep, and the microcontroller keep working as expected, but just jumping the loop, the infinite loops, which again can bring a lot of security vulnerabilities. So with these results, we were able to understand what is going on in the microcontroller. So we go further. Because we have the full system. We even have the standard cells that are being employed to implement this microcontroller, all the digital blocks. And by doing that, also we are also understanding what is happening to the architecture of the microcontroller. We notice that, of course, the sequential standard cells like latches are the ones that are failing when we are decreasing the energy of the supply, what they are the ones. But you also notice that there are some issues going on also in the bus during the bus protocol. So here this the setup of the glitch attack. So we are injecting attacks using the FPGA within the chip whisperer FPGA board, and we also reading, trying to read the input of to read some data using the SPI of the microcontroller when we are attacking, and we also synchronizing the clock of the board that we're using to attack on the microcontroller. So we even went further and we improved the attack, the glitching attack circuit that is implemented within the chip whisperer. We noticed that by adding some additional transistors to modulate the energy better than the feeding of the attack of the glitch, we will be able to see when the microcontroller is failing, and also have control. We can also have control of the latency of the glitch. So here is some pictures of the setup. We are using the board that we use to characterize our microcontroller, and the glitch generator. We put all that together and add some, as I say, we add some additional transistors, which are here in the product board. So here is the glitch wave of the first circuit, where we don't have the footer transistors. So we are showing here that the glitch can go all the way down to level 0 and come back. So here is also that we are able to have attached as fast as 10 megahertz, glitches as fast as 10 megahertz in different domains. But here we are focusing on the digital domain. So here are some results of the glitches that we employ. Particularly, we are here plotting hundreds of successful attacks in different frequencies of the glitch, for different frequencies of the glitch, and also different glitch durations. So to see what is the spectrum of those glitches attacks. Again, here we are taking the attacks between 1 megahertz and about 40 megahertz, which is about the frequency, the nominal frequency operation, the range of the nominal frequency of the microcontroller. So we can see that in the nominal frequency operation range of the microcontroller, we have successful attacks in each frequency. We call successful attacks when we are able to break the loop and keep going, keep the operation going on the microcontroller. These are the results with the improved circuit of the attack. So now we are able to have better control of the signal energy, of the glitch energy. By doing that, we are able to see how much glitch we need, and also to go to study better what is going on in the circuit at the circuit level on the microcontroller. Here we are plotting for 9 different frequencies of the regular operation of the microcontroller. And here we're showing different amplitudes of the glitch attack that go from about 800 millivolts all the way to the nominal voltage, and also plotting the energy of the glitch within each frequency of the attack. Just by checking the mean of the glitch, the energy of the glitch, we can see what will be the voltage sensor that is required in order, for instance, to chill the microcontroller against these kind of attacks. That's one way to think of a solution. But again, there are different potential solutions in order to avoid this kind of attacks. The good thing here is, as I mentioned, is that we are using a microcontroller that we know all the details of the microcontroller. We know the architecture, we know the circuit level from the GPIO, from the regulators, all the way to the core of the microcontroller. By having that kind of details, that kind of knowledge, we can even study, and by doing those attacks, we can know what's going on the system. This is kind of a new reports compared to the reports that are already in the literature that they report this kind of glitch attacks, but in commercial system on chips or commercial microcontrollers, where they don't know many details of the microcontroller. Again, having this kind of control, we can also understand what will be the least energy required to attack the microcontroller. This is a summary of the number of results that we have when we are doing the glitch attacks. Okay, with that part of the presentation, we have different kind of solutions for this kind of glitch attacks that still we haven't published, so we are not presenting it here. But we can tell you that there are different there is a need for different solutions in hardware, not just in architectural level, but also in circular, in order to protect a single microcontroller that will be the brain of a sensor network that is connected with a bit system like a power grid. So this kind of vulnerabilities will increase with the knowledge of these kind of devices, and you will see in the future additional attacks and even a diverse type of attacks in hardware. So now we're going to try to change a little bit and change gears to the encryption accelerator, which is another part of the system for a secure system where you need to secure the data, you need to protect the data. So we're going to talk about AES 256-bit accelerator that was implemented and measured within the group, and to show you what are the issues in order to implement this kind of accelerator for low energy IoT sensors, like sensors that are currently deployed and they will be deployed, like in power grids, in transportation systems, where those kind of sensors will be low cost and even low energy, or they will be supplied by energy harvested sources. So here in a system on chip, we need to focus when we are talking about encrypting data or moving data within the system, within the microprocessor and the memory, or even from the microprocessor to the external world. We need to focus on the limiting issues for energy efficient accelerators, and this is true even for all the current trend in AA accelerators, like deep neural network accelerators within the chip. So here we are showing the relative energy cost on the y-axis, and in the x-axis we are showing the different parts of the systems, from DRAM, which is going to be the external, all the way to, for instance, the ALU. In this case, the addition within the logic unit. So for going from, we are here putting in base the logic unit access. So going to the register within the logic unit will take 1x energy cost, and going just to the register file, which is there close to the core, will take 10 times the energy cost of the data transportation between the core and the register file. Now we are talking about just the multiplication instruction will take 30 times, and this run that is close also to the core within the die will take 50x. So it is not easy to implement an accelerator, a data encryption accelerator that requires, um, for instance, to go to get access to the SRAM access. So it is not easy to see encryption model in low energy sensors that will be implemented outside of the microcontroller. Right now, most of the sensors, the low energy sensors that are running this kind of encryptions in software. We know all the vulnerabilities in software, but again, we are not talking about software. We're not talking about hardware. Again, the issue with software is the cost is going to be higher. Just thinking here that just for DRAM, the cost is about 6,000 times. So software based will be about that or more than that. So we need to have the energy cost within 10 times or 50 times in order to be able to have encryption, this kind of encryption engines like 250 CBICs within a low energy sensor. So this is the AES that we implemented. So we implemented the AES um, with close to the core. So again, just imagine now that if we do implement it outside of the core, we're in a peripheral within the APP bus. So the goal again is try to have data transportation close to 10 times. And if we are talking about putting the mode accelerator farther away, like in the peripheral bus, we cause an additional, as we are showing here in this slide. So again, we are focused for this AES. We are focused in an ultimate architecture that reduces memory access in order to improve the energy efficiency and is close to the core. So here we showed that we, in order to do this, we need to design a pipeline architecture. That where we are asking that at setting the flows, but concurrently. Here we go through a nonlinear matrix multiplication in order to get it. But this kind of pipeline accelerator still has some energy issues. So we decided that we need to have different kind of stages. So here we are showing that we implement a system with one state pipeline, one Xbox accelerator with a local table, or in order to do comparisons and see how we can improve energy efficiency. This unit was including an SBOS custom instruction inside of the microprocessor, and we also use it inside of a custom AES core, which over here by having a direct memory access. We perform instruction execution for analysis and memory access by only accelerating the SBOX. The memory access sure was reduced, but it was reduced just a little, as we shown here in this figure. And this reduction was not significant, and the execution SBOX only reduces around 10% of the load instructions, so we need to look for different solutions. So this, in comparison, what it is shown in the literature, is what most people do. They do acceleration, but they don't understand that, again, the data transportation, they don't go all the details, is costly. Including this data, this penalty energy will, at the end, will not result in a lot of benefits. Let me check the time. This is the architecture of the AES core. Includes a data memory access, the one that we implemented to push the block, to close the block from ciphering, and also by being able to use it as a standalone memory made AES engine. The DMA automation is provided with a state machine for reading and writing chunks of 128 bits from the memory. This procedure of reading and writing is monitored by several counters, so we are able to have control of what is going on the transportation data. We did design the energy consumption of the core reaches about down to 1.5 nanojoules, one optimal at the optimal frequency of 3 megahertz, and using a supply voltage of 0.4 volts. So these results using the custom instruction were capable of achieving a 2 times energy reduction, and a memory map core reaches about 300 times. And the DMA inclusion, the memory access mode inclusion makes the design to be pushed up to 100 times in the overall system chip. So in the result, we have compared to some results, 2.5 times better performance than what is posted in the literature. So again, here we are emphasizing on energy consumption of inclusion model. So as we point out in the first part of the presentation, we need to focus on different parts of the hardware, not just on the vulnerabilities attacks by software, but also all those circuits and all those systems to secure data, to secure the chip, need to be low energy. This was fabricated in 100 nanometers. Here we show details of the different. So now let's jump down here to a different instance of hardware security instance, which is the physical uncountable function. In this case, we're going to show an NVRAM path. So what is a physical uncountable function? Here in the circuit, we are showing that a physical uncountable function has a challenge and a response. So for each challenge, it has a response, and these challenge and response pair are quite unique. So you can use this kind of unique pairs as an identifier for a chip. The response of a good path is usually characterized by being random. That means that we need to have the same probability of having ones and zeros at the output. And a unique path generates a different response to a given challenge. So these features allow us to use paths to generate, for instance, reliable and stable encryption keys, like, for instance, to be employing the AES-256 encryption model. And therefore, it is relevant to pay attention to the implementation of physical path. So just imagine now that the path is not low energy, is not reliable enough, and also it's not secure enough. you are having an additional hardware vulnerability. So let's check about the prior art. So several reported path design methods, such as SRAM path, free oscillator path, or even hybrid path, acquire key outputs by amplifying signals from random physical properties. For instance, some properties are the most common ones are the propagation delays, like, or even the jitter in an oscillator, and the metastability of the latch, or even the threshold voltage. One of the issues is that this path under certain conditions, for instance, of temperature or supply voltage, or even process variations, they should generate unique, random, and stable response. But we know that these random physical properties are amplified. So what we use this kind of variation or these conditions in order to amplify it. But again, we know that these kind of variations also limit the reliable output of the path. So we will see later on what I meant for this. So again, this variability of these different conditions make an stable keys. So a key for a given voltage, like a 1.2 voltage, for instance, will give you a different key from 1 volt or 0.10 volt for the same challenge, which this will give you an unreliable key for instance, for an encryption engine. To solve these problems, particularly the stability, there have been methods in the literature for stabilization. For instance, in this case, um, people had shown that by using employing the outside breakdown mechanism, you might be able to harden the key bit. So once you have unique enough unique bit by post processing, then you will be break down the outside in order to have a stable keys. But this has a problem, right? So this kind of keys will this kind of key will be able are exposed to a physical attack. I can go and do some decapping of the chi, and but just seeing at the chi, I will be able to see the key just by applying even imaging techniques. Taking into account these stability issues, we have proposed a path design based on a floating gate, no volatility RAM, which doesn't lose stability due to variations in environmental conditions, and uses a method of stabilization that doesn't present physical changes that could be explored in an attack of the path key. So we are employing the capability of recording or better to storing the key within the same macro. So with this, we achieve a stable path design, reliable enough for encryption, key generation, and authentication. So this is the floating gate non-volatile RAM path cell design that we use. Again, we are using a floating gate based non-volatile RAM. The path key bits are obtained by converting the computing result of the accumulated charges into in the two floating gates of the cell. So here we have charges in the two differential floating nodes. Since during the process fabrication we have ionization, so this kind of ionization might change the number of charges of these floating gate nodes, and therefore we have a kind of random source of data. So the logic state of the differential cell will be determined by the difference between the number of charges stored in the two floating gates and the differential current finally generated by these two charges, as shown in the figure as current I1 and I2. These cells can be electrically locked, protecting our stable path key from writing. So we are able even to go and protect the cell for writing by using some digital operations. So again, we demonstrate that we can obtain path key bits from this from the raw fabricated cells, and after and after measuring and post processing these cells, we are able to store a stable key. So we will show you how this works. So the proposed process of this, we to generate a reliable path key, first we read the raw keys from the path output, and then post process these keys, and later on write back the key into the cell, and finally we block the cell for writing. So with this, we have a reliable path key and a stable path key. So again, as I say, we read the path to get the raw key. And this mechanism that we are using is the competitive mechanism of the store charge during fabrication, which produces a differential current within the cell that is read. And this reading by columns in the macro is read by and amplified by a large sense amplifier. So after reading the cells repeatedly, so we read many times the path key of the cells just for statistical reliability. And then we notice that there are bits that are not stable. So we call this here unstable bits. So we need to do something with these unstable bits. Let's see, for instance, we are going to show that after 200 or 300 reads, 20 or 5, actually 5 to 20% of the reads have different values, and therefore with unstable bits then needs to be stabilized. So therefore we need post-processing in order to stabilize the key. So we use two post-processing methods. One is called temporal majority voting, and the other one an up-down counter. So the first one, the majority voting, consists of calculating the model of the data in a time window to find the turn of the bit and stabilize the bit value. So for instance, here we are reading 5 different values, and we go moving this window in order to calculate the major appearing value, and then stabilize the output data. The thing is, with this method, not all the bits are completely stabilized, as we shown here in the output. So we need to do an additional post processing. We employ another method, although that method works, has a good statistical data. We use another method. This is up-down counters. So how it works? We have a counter of MA bits. In this case, we're using 5 bits, 6 bits, 6 bits, which starts in the middle of the range. So we start in the middle range, in this case, to the M-1. And we start decreasing counter if the B read is 1, or decreasing if the B read is 0. So here we show that we are going to the reading path outputs, and finally the counter will reach the value of 2 raised to n power, which means that the B is 1, or 0, which means that the B is 0. The up-down counter method can be run indefinitely until the PAM value is resolved, so it will depend on how you take the decision. This post-process key now is stable with these kind of methods, and now we need to write back to the NVRAM cell. Writing the key into the cell and taking advantage of the volatile capacity to store the stable key, we have a reliable and stable key. And finally, the cells are locked to prevent programming attacks and to maintain the security and stability of the key. Now the hardened path piece don't show any physical changes that might be exploited by imaging techniques, because just by writing back the data, you are not changing, or you are not breaking down the size as in previous works. The macro was implemented in 180 nanometers standard digital CMOS. And this macro, as we had shown, has been tested and measured. These are the measurement of the raw kits. Different values. In this case, we're showing the values are nominal conditions, but also at different supply voltages. We performed 2,000 readings of the PAF cell, which yields about an average of about 2.4% on a stable bits when we are talking about the raw keys. Then we calculate the number of ones generated in bit stream for 6 measured chips, and found out that the average normalized Hamming weight is about 0.48 with a standard deviation of 0.15. Here we're showing the result for the post-processing of the raw keys using 5 and 7 and 11 bit windows obtaining better results, of course, with the largest majority voting bit number of windows. So as again, we showed that the TMB was not completely enough to stabilize the bit, so we use the up-down counters, which solves for all the bits completely. Finally, we report 100% stable and reliable keys, because again, we are writing back the data and locking the data, so users will not be able to change those keys. And this path also can be used in low power systems applications, like in low energy sensors, which is the idea of the talk that we are showing here, that this kind of path is, or this kind of security instances are ready to be implemented in low energy sensors. Okay, so just I think it is time to summarize the talk. We know meltdown and spectre. These are two well-known vulnerabilities discovered by Google in Intel microprocessors. And people have been saying, okay, this is low to medium security risks. We know this kind of security issues were raised by architecture vulnerabilities, which can be classified as hardware vulnerabilities or hardware security issues. Now let's imagine the network sensors that we have, the quantity or number of devices or sensors that we have right now. There is an estimation, as I said before, of 25 billions of devices, of things, of sensors interconnected. So the security risk, again, we can say that is in the middle, because we don't know many details of the implementation, or better, the attackers are still knowing details of the implementations in order to attack. But here I'm just showing a possibility of an attack for an infrastructure where we are using a lot of IoT sensors. Currently, for instance, the power grid that we have installed in our countries, they have tons of SCADA systems and also sensors that are deterring automatic operation. So now just imagine that one of those sensors can be attacked, for instance, and take down 2 or 3 main generators within a country, within a system. This will provoke completely fail of the power grid system, and a country, in a full country, can be completely down in power supply. So the summary is, or the takeaway is, that we require further hardware and software solutions to avoid this kind of high risk events. And again, as I showed in the first part of the presentation, there is too much to discover within hardware, vulnerabilities of hardware that are rising, and even, as I say, is in the case of the ones that we apply here for microcontrollers, that they were supposed to work in operational conditions, but once we start changing and moving things here and there, we notice that there are vulnerabilities in not just circuit level, but also in hardware level. So we need to start proposing solutions in all areas. For instance, in the standard cells, in order to blind all these kind of system architectures to future attacks, or future attacks that will be known by attackers. With this, I want to acknowledge my undergrad students that have been working on this area. Luis Rueda, Cristian Duran, Felipe Castro, Diana Cepeda, Karen Flores, and our alumni, Javier Ardila and Hector Gomez. I also want to thank Ciencias for partially supporting these kind of projects, and also Sci-Fi for providing access to fabrication. These are the contact details in case you want to have further discussion about this topic. Thank you so much.
So thank you very much, Elkim. So now we are open for questions. So if you want to do any question, please do it using the YouTube chat channel as soon as possible. So we have now one question here by Amnol Singh Narwaria. I don't know if I'm spelling correct. So thank you very much, Amno, for your question. So Amno is from IIT Hyderabad in India, and his question is reliability and remaining useful life of IC is also major concern in hardware security domain. So I want to know how to find age or RUL accurately.
Yeah, that's definitely a good question. This is a well-known issue with in the defense system. So they try to put monitors, aging monitors, in order to decide when the system should be in operation. So aging monitors will be able to let you know if the system will start failing, and those kind of failures, again, as Ahmed pointed out, might open to new vulnerabilities. So the short answer is that yes, we need an additional hardware instances to measure aging within the chip.
So I'm seeing no more questions for the moment. So if you have a question, please do it as soon as possible. So I have one, Elkin.
Yep.
So how you can see the compromise between all these extra secrets to cope with security attacks and so on, and also considering power and extra area and so on.
Yeah, it's something that we need to start dealing with. Because we need to deal with security, we need to start paying for this kind of new these penalties, area penalty, energy penalty. So how to deal with that? Again, is in our hands, in the circuit designers' hands. So we need to bring solutions, low energy solutions, low energy solutions, efficient solutions. So we are not now selling security instances instead of functional chips. So this is kind of now one, for instance, in the case of two random number generators, physical and countable functions, encryption models. This is a hot topic right now for trying to decrease the energy consumption of these models, and also the area, in order to be able to implement in low energy and low cost sensors. So it's currently a major trend, and people is discovering and bringing up new solutions to this. So it's an open problem.
Thank you. So people are a little bit ashamed today, so there is no more questions by the audience. But I have another point that so we are seeing nowadays a lack of integrated circuit around the world. So many industries stop now because they don't have the chips to include in their products. For example, here close to Porto Alegre, there is a General Motors plant, and since several months they are stopped because they don't have the necessary chips to produce their cars. No, so this is one example of the increasing of the need of microelectronics chips around the world. So, in your opinion, what people in Latin America can do to help in this situation?
Yeah. This kind of um, problem that we are facing right now with the the um, the lack of enough fabs to produce these microchips, then it's part also of the economy, right? It was not common for plants like General Motors to have to produce to buy a lot of stock chips or stocking a lot of chips because it was incompetency. So they were just using the chips or buying the chips that they were requiring. This translate um, to the fabbing and also to all the I would say the design, the process from the design all the way to the fabrication. That that is every time it's becoming higher and higher. So because it's becoming higher and higher, so cheap new chips, new chip wins, new chip fabrication is becoming also highly cost. So what we need here are solutions to decrease this kind of cost in all the chains. So in this case, from designing all the way to fabrication. In our area in circuits, and also in CAD and software for to design this kind of circuits and to verify this kind of circuits, there is a lot of work to do. So what I encourage the Latin American students is try to to that are working on electronic engineering to go further and understand these kind of challenges and try to solve them, because these kind of solutions will be reflected all the way to the economy, like in this case, to decrease this kind of shortage.
Okay, thank you. Yeah, I think there is a lot of opportunities increasing in Latin America, no? Because there is a lack of people with the skills to design chips and to produce EDAs around the world. And for example, we are seeing an action nowadays here in Brazil, where companies like Silvaco, that is based on USA, they have also a branch here in south of Brazil, in Porto Alegre, Rio Intent, now in Silica, also HCL in Campinas, that is former NXP and former Freescale. So all these now, they are engaging people. Also Chipos in Santa Catarina, that is a designer house that also have offices in representation in USA and Switzerland. So all these companies, they are engaging people, no? So there is a great opportunity for Latin American professionals and students to see microelectronics and EDA as a good opportunity to work now and in the near future, no?
Yeah, definitely. And I want to emphasize that that due to the pandemic, it is becoming for our work that is circuit design, it is becoming relevant the remote work. So most of my friends that work in this area in circuit, and I guess in Silica, the Silica that got the people from Zetec, there are working remotely as most of the circuit designers in the world. So also my friends that are working on the Silicon Valley, they're still working on remotely, and they're able even to put same output or even more output in that area. So So circuit design, as Professor Ricardo, and not just circuit design, CAD design, or all these architecture design is becoming even more relevant in current situation like pandemic. We know this shortage because um, um, the need for consumer electronics to connect from home. Um, so it is more relevant to find skilled people in the world that work in this area. Why Latin American is can be definitely a key player in in this area. I will say that we have wide number of schools in South America that are pushing hard in order to in electronic engineering and graduating smart people. So with I believe that we might see within the next 2, 3, or 4 years a new yeah, how to say a new source of microelectronics in America, as Professor Ricardo Reis pointing out, in silica coming to Brazil. And I will say that that maybe within 1 or 2 years will that list that Professor Ricardo just mentioned will duplicate easily.
Okay, thank you. I forgot to include also in this list, for example, Synopsys in Chile, Cadence in Belo Horizonte. So all these companies on microelectronics, they are engaging people now, and they are going to keep engaging for several years. So if some of you that are attending this very nice talk by Elkim today, you should strongly consider to become a professional in chip design or EDA design, and because there is a very nice opportunities, no?
Mhm.
So thank you very much, Elkin, for this very interesting talk today. And so your talk, as all others, were recorded, and in few weeks, the recorded version will be available in our YouTube channel. And so now just to remind you about next events. So I don't have the flyer now here of next week, but before that, if you want to attend a talk that I'm going to do myself today, virtual one, in the event celebrating the 13th anniversary of the IEEE CASS chapter at Uni in Peru. This will be today 4 p.m. Peruvian time. That means GMT -5. And after my talk, sorry that I didn't include here, there is a talk by Professor Carlos Silva from Peru and another one by Professor Fernando Silveira from Uruguay. And next week, I don't have the flyer yet, so we are going to have a talk by Professor Cláudio Diniz from Federal University of Rio Grande do Sul. He's going to talk about approximate hardware accelerator for video coding, and you should receive the email information, including his short bio and the abstract of the talk, still today. And I hope to get all you in the session next week, 1:30. And then the week after, we have 2 talks. One will be the first industrial talk in 2021 with Alan Wong from Insilica, UK, talk about enabling the next generation of always connected cars. And in this session will be also announced the establishment of Insilica in Brazil at Porto Alegre by Dr. Júlio Leão. So it's very nice to see that it's increasing the number of microelectronics company in the region. You can also see 20 industrial talks that were done last year with very interesting presentations from companies from Brazil, Argentina, Costa Rica, Chile, and so on. and you can have a nice overview of some companies working on microelectronics in Latin America. And for example, in the talk of NXP by Sergio Dueñas, there is an information about the projects they have done a few years ago of a circuit to control the engines of cars. And this chip is being used in all Formula One race cars nowadays, and also in NASCAR ones. So this is just one example of interesting. And then we are starting next July 22 this season 2021 of Industrial Talks with Alan Wong and in Silica. And on Friday, July 23, Dr. Vladimir Alves that is a CTO at NGD Systems. So is going to talk about computational storage and its applications for machine learning. So I hope to have your audience also in the next weeks, because we have a very interesting talks also. So thank you very much to all you to attending this very nice talk by Elkim Roa today, and see you next week for the talk that will be done by Professor Claudio Diniz. Bye-bye. Have a nice weekend.
Bye. Thanks so much.